Dear students, this is the lecture number 5 and we will continue the separation axioms. So we start with some basic theorems. So here is the first result. So a subspace of a Hausdorff space is Hausdorff. Now the proof is simple. So let X be a Hausdorff space and Y be a subspace of X. So let 2 point X comma Y belongs to Y. We need to prove that Y is Hausdorff, right? Now since X, Y belongs to that topological space Y, so this is also in X. Now since X is Hausdorff, so there exist open sets U and V in X such that X belongs to U, Y belongs to V, and U intersection V is empty, right? Now that will imply X belongs to U intersection Y, Y belongs to V intersection Y, both open in Y and their intersection is empty. Right? So that implies Y is also Hausdorff. So this proof is simple one, right? Now the next theorem is a product of Hausdorff spaces is also Hausdorff. Now there is the next theorem. So a product of Hausdorff spaces is Hausdorff. So in product topology, just remember that whenever we say product of some spaces, then we always consider the product topology. So if the topology is box topology or uniform topology or something like that, then we always mention that. If we do not mention anything, that means you have to assume that the topology is the product topology. Here is the proof. So first of all, let that collection X alpha, say alpha belongs to that lambda, be a family of Hausdorff spaces. And we claim that the product X alpha is Hausdorff. So we choose two different points from this topological space, right? So let x, which is just x alpha, and y, which is just y alpha, belongs to this product. That's mean that x alpha belongs to that capital X alpha. Or in other words, x alpha, y alpha both belong to this for all alpha belongs to lambda. Right? Now since x not equal to y, that's mean there exists a index beta such that x beta not equal to y beta. So there exists beta belongs to lambda such that x beta not equal to y beta. Right? Now it is given that each x alpha are Hausdorff, right? Now since that x beta is Hausdorff, so there exists u beta and v beta open sets such that x beta belongs to u beta, y beta belongs to v beta, and u beta intersection v beta equal to empty. Right? Now let u equal to that pi beta inverse u alpha, so u beta, and v equal to pi beta inverse v beta. That is, what is my u? That is u equal to some x, that is I should not write in this form. That's mean it is just the product of x alpha, or you can write in this way, it's product of u alpha, where u alpha equal to actually x alpha, where alpha not equal to beta and equal to u beta, or it is clear, right? We can just assume that, where this. Okay. Now it is clear that, so obviously that imply x belongs to u and y belongs to v, and both u is my u and v are open in this product. And also u intersection v is empty. Why? Because u intersection v is just, because u intersection v is just the product of u alpha intersection v alpha. Now since we know that at least we have one index beta where u beta intersection v beta is empty, so this is empty. Intersection v beta equal to empty. Right? So product of x alpha is Hausdorff. Now we prove that a subspace of a regular space is also regular. So here is the statement. So a subspace of a regular space is also regular. This proof is also simple, just use the basic definition. So first of all, let X be a regular topological space and Y be a subspace of X. So first of all, we need to show that any single point, that is single point set in Y is closed, and this is trivial, right? Now let X belongs to Y. Now since X is regular, that singleton X is closed in X, therefore we can write singleton X as singleton X intersection Y as well. Now this is closed in X and this is intersection with Y, therefore that singleton X is also closed in Y. So first condition is satisfied, that is any single point set in Y is closed. Now we satisfy the second property. Now let X belongs to Y and B be a closed set in Y. Now since such that X not belongs to B, right? Now since B is closed in Y, that imply there exists, or we can write just there exists closed set, say C in X such that B equal to C intersection Y. This is the definition, right? Now claim that it is easy to see that X does not belong to C. Why? Because if X belongs to C, then X belongs to B, as we already have X belongs to Y, right? Which is a contradiction. That's mean X does not belong to C. Therefore, X belongs to X and C be a closed set in X. But given that X is regular, now given that X is regular, therefore there exist open sets U and V in X such that X belongs to U, that C subset of V and U intersection V is empty, and this imply U intersection Y and B intersection Y are closed in Y and their intersection is empty. Right? And X belongs to U intersection Y and my B equal to C intersection Y subset of B intersection Y. Right? So we get two open sets, this and this, two disjoint open set because they are disjoint, and one contains X and other one contains B. Right? Therefore, Y is regular. Now we prove that a product of regular spaces is also regular. So a product of regular space is regular. Here is the proof. So let again X alpha be a family of regular spaces, right? Now since each X alpha is regular, therefore each X alpha is Hausdorff as well. Right? Now that will imply product of this X alpha is Hausdorff. Now since this product is Hausdorff, so the singleton point set is closed. That imply that singleton point this, which is just X alpha, is closed in that product. Right? So the first property is satisfied. Right? Now we move to the second property. Here to prove this result, that is to prove the second property, we will use the lemma which we proved in the last lecture. So let X be an arbitrary point in X, in that X means product of X alpha, where X is just X alpha. Okay, and let U be an arbitrary open set in X alpha, this product of X alpha containing X, that is X belongs to U. Now to prove that product of X alpha is regular, we need to find, so we need to find one open set V in that product such that X belongs to V and V closure subset of U. Right? Okay. Now since X belongs to U in the product topology, So there exists a basis element this kind of basis element u alpha such that X belongs to that product of u alpha subset of u. Now since we are talking about the product topology, so we have u alpha equal to actually X alpha for all but finitely many alpha. Now so let for alpha equal to alpha 1, alpha 2 up to alpha n, for this finite value u alpha is not equal to X alpha. That is, u alpha is proper open set in X alpha. Then for each alpha equal to alpha 1, alpha 2, that alpha n, that X alpha belongs to u alpha and X is regular, X alpha is regular. Therefore, there exists V alpha, say open set V alpha in X alpha such that X alpha belongs to V alpha and V alpha closure subset of U alpha. Right? That was the if and only if criteria for the regular topological space. Fine. Now if alpha not equal to that value, that is alpha 1, alpha 2, alpha n, then choose V alpha equal to X alpha. That is the whole space. Now let V equal to that product of V alpha, this. Then obviously V is open set in this product. Why this is open? Because for all but finitely many values of V alpha is the whole space, right? Also, X belongs to V, right? Because each X alpha belongs to V alpha for all alpha equal to alpha 1, alpha 2, alpha n, and even if alpha not equal to this finite value, then it is the whole space. Therefore, each X alpha belongs to V alpha. That means X belongs to V. And V closure, which is just product of V alpha closure, right? And each of these V alpha closure subset of U alpha, right? So it is subset of product of U alpha, which is subset of U. Right? So we get this kind of open set V such that X belongs to V and V closure subset of U. Therefore, that product of X alpha is regular. Note that we have used the fact that Hausdorff implies one point sets are closed. Actually, I proved this one in the class. So if you don't remember the proof, again I can give a proof of this one. The proof is very simple. So given that X is Hausdorff, right? So given X is Hausdorff. Now let X belongs to X and claim that, or we need to prove that singleton set X is closed, right? But it is easy to prove that, that is X minus singleton X is open. Now which is equivalent to this, or we can write here. So this is equivalent to this. This is open, right? Now let Y belongs to X minus singleton X. That imply X not equal to Y. So X and Y are the different point in X, and given that X is Hausdorff, right? So that imply there exists U and V such that X belongs to U, Y belongs to V, and U intersection V is empty, right? Now that imply V subset of X minus U, which is subset of X minus singleton X. So that imply Y belongs to V and V subset of X minus singleton X. So we choose one arbitrary element from X minus X, that is this set, and we find one open neighborhood containing Y such that V subset of X minus V. So here we can write this is open sets, right? Right. Now that imply X minus X is open, that is that singleton X is closed. Okay. So now we will prove that the topological space RL is normal. See theorem. The topological space RL, that is the lower limit topology, is normal. Okay, here is the proof. First of all, we need to prove that any singleton point is closed. So let a point X in R. Now what is the complement of X? What is my R minus X? R minus X is just minus infinity comma X union X comma infinity, right? And both are open set in RL, because now minus infinity comma X and X comma infinity both are open in R, in lower limit topology. Why? Because RL contains all, or you can say that open sets basis elements of RL are of the form that AB and this, right? Okay. So therefore R minus X is open, therefore that singleton X is closed. We can write just RL. Okay. Now we need to prove that it is normal. So we choose two disjoint closed sets, and we prove that disjoint closed sets are separated by the open neighborhoods. So let A and B be two closed sets in X. Okay. Now claim for each X in A there exists basis element say X comma some write Y such that X comma Y intersect B is empty. So we need to first of all prove that for each point there exists an basis element. So this is also simple to prove that. Why? Because since X belongs to A, right? And what is my A? Now here, and we can write an A intersection B is empty, therefore A subset of X minus B, right? That implies X belongs to X minus B. Now B is closed, so X minus B is open. That implies there exists basis element say X comma Y such that X belongs to X comma Y subset of X minus B. Now that implies that X comma Y intersect B is empty, right? Similarly, for each point in B, we can get another basis, this kind of basis element, which is disjoint from A. Okay, now we are ready to prove this theorem. So, for each A belongs to A, there exists XA in R such that A XA intersect B is empty, and also for each B belongs to A, there exists say XB in R such that B comma XB intersect A is empty. Now let U equal to union of all of this element A comma XA, and V equal to union of this B comma XB. Okay, then obviously U and V are open in RL, right? And A subset of U and B subset of V. Now we claim that U intersection V is empty. Now claim U intersection V is empty. Why? So if possible, so let Z belongs to U intersection V. So what is my U? This is my U and this is my V, right? So Z belongs to U means, so that imply Z belongs to U, right? That's mean Z belongs to this. So therefore, so there exists A in A such that Z belongs to that A comma XA, and also Z belongs to V implies so Z belongs to V implies there exists B belongs to B such that Z belongs to B XB, right? And this will imply AZ subset of X A comma XA, and this will imply BZ subset of BXB, right? So that is, okay, I am writing again. So there exists Z in R such that A Z subset of A XA and B Z subset of B XB. And we know that this one intersect with B is empty, and this also, and this one does not intersect A, right? Now if possible, now if A less than B, then what is my claim? See, so Z belongs to A comma XA will imply A less than equal to Z, and Z belongs to B imply B less than equal to Z, right? Now if A less than B, then you can write here, if A less than B, then A less than B less than equal to Z, that imply B belongs to AZ subset of A XA, and this is the contradiction, right? Now this is a contradiction. Why this is a contradiction? As B belongs to B, but because we know that this set does not intersect B. Now what is the other case? Now if B less than A, then we use this one, A less than equal to Z less than equal to B less than A less than equal to Z. Therefore, A belongs to BZ subset of BXA. Again, this is a contradiction. As A belongs to A and this BXA intersect A is empty. Okay, so we get this is non-empty. So thus we have two open sets U and V such that A subset of U, B subset of V and U intersection V is empty. That implies RL is normal. Okay, so these are all about the regular and Hausdorff topological spaces. So in the next lecture, we shall see some results on normal topological spaces. But here at the end, I just want to note one results. This one, that is RL cross RL is not normal. Anyway, here even in tomorrow, that is in the next lecture, I will not prove this one because the proof of this theorem is little bit complicated, but one can prove this easily by the Eurasian lemma. So I am planning to do the Eurasian lemma first, and then by using that lemma I will prove this theorem. Anyway, for a time being, just assume that RL cross RL is not normal. And if you know that RL cross RL is not normal, then it serves two purposes. The one purpose is regular does not imply normal. Why? Because we have seen that RL is normal, right? That implies RL is regular, right? Now since RL is regular, and we know that product of the, in fact we know that arbitrary product of regular spaces is regular, right? Therefore product of two regular space is also regular, right? Therefore RL cross RL is regular but not normal. So therefore regular topological space does not imply normal topological space. So this is the one observation. And another one is, see, for the Hausdorff cases and the regular cases, we have seen that subspace of a Hausdorff space is Hausdorff, product of arbitrary number of Hausdorff spaces is Hausdorff. Similar result we proved for the regular spaces as well. That is, subspace of a regular space is regular and product of, in fact, arbitrary product of regular spaces is regular. But that type of results is not true for the normal cases. That's mean subspace of a normal topological space may not be normal, and product of two normal spaces may not be normal. And this is one example, that is RL cross RL, that is not normal, right? That's mean product of two normal spaces may not be normal, because we know that RL is normal, but RL cross RL is not normal. And another thing is the subspace of a normal space may not be normal. And for this result also, so for that one also we need some tools which we do not know. Therefore, I am planning to do some results on normal topological space, and then I will come back to that two properties, that is product of two normal space may not be normal, that is the proof of this theorem, and the subspace of a normal space may not be a normal topological space. Okay, so today we stop here. See you on the next lecture.